Hello, Engineering 2000. So, today's topic will be ceramics. We're going to spend probably a lecture and a half or two lectures on ceramics. You should have reviewed the applications of ceramics in engineering prior to watching this video. If you haven't, go ahead and take a look. There are such a plethora of applications from aerospace to electronics to mechanical to civil to biomedical. Um, it's important that you appreciate just how necessary and how utilized ceramic materials are um, for most engineering solutions. Okay, so what are ceramics? We're talking about compounds that whose properties fall somewhere in between metallic and non-metallic elements. And the key word there, compounds. So we have bonds. Our compounds need bonds to be compounds, and the predominant bonds here are ionic. Sometimes there are covalent bonds as well. And the traditional ceramics include china, porcelain, bricks, tiles, glass, and so on. And as we indicated earlier, you should have looked at some of the more modern uses of ceramics based on your own research. So for this module, we'd like to be able to describe the unit cells for the most common ceramic material. We'd like to be able to predict the crystal structure of ceramic materials based on knowledge of the chemical formula and the ionic radius. We hope that you will be able to name and describe 8 different ionic point defects, describe being the key word, that are found in ceramic materials. There is significant scatter in the fracture strength of identical ceramics. We should be able to understand and explain why after going through this module. There's a property called the flexural strength that is used to compare the sort of the bending ability of ceramic materials, and by the end of this module we expect that you will be able to compute this flexural strength based on certain input from a series of tests called 3-point loading tests. And remember, we spoke about slip several weeks ago. We'd like you all to understand how, from a standpoint of considering how slip occurs, explain why ceramic material are normally brittle materials. Okay, so the crystal structure of ceramics is quite a bit different from that of metals, and the primary mechanism that drives that difference is the cation anion bond. Right. So if you remember, cations are of course positively charged atoms, and anions are negatively charged, so they have gained an electron. Right. Some of the sort of rules or the constraints that influence the crystal structure would be the following. The crystal structure must be electrically neutral. The cations and anions, the fact that they are of different sizes, that will sort of particularly influence the crystal structure. Also, the fact that they may have different magnitudes of electrical charge, and that is also significant in determining the response of the crystal structure and the geometry as well as the size. Now, cations are usually smaller than anions, so we define the ratio RC over RA, where RC is the radius of the cation and RA is the radius of the anion. So clearly, if the cations are smaller, that ratio is less than 1. Now we'll see that that ratio plays a role later on in terms of having some type of influence on the stability of the cation anion bond. Okay. Also, just like before, where your atoms for your metallic bonding liked to bond with as many nearest neighbor atoms as possible, With the ceramic crystal structure, it's very similar, but we're just talking about the ions. Now, we'll be talking about the ions in terms of preference for nearest neighbor ions. So the cation would prefer as many nearest neighbor anions and vice versa. So if we take a look at figure 12.1, we can see that let's say you have a cation which is smaller than the anion. So let's look here. We have a cation which is in contact with 4 anions. If let's say we were to reduce the size of the cation but maintain the size of the anions, we see at some point that the cation could no longer contact the 4 anions. So if it's not in contact with the anions, then it's more stable. It's more unstable because it's sort of free to float around here. Okay. So recall the coordination number from eons ago, or let's say maybe 5 or 6 lectures ago, or perhaps 5 weeks ago actually. So that would be about 15 lectures or so, or 10 lectures or so. Alright, so but recall the coordination number. We talked about the number of nearest neighbor atoms. In the case of ceramic bonds or ceramic crystal structures, we're talking about the number of nearest neighbor ions. Alright, so that coordination number would be related to the ratio of RC over RA. Because we saw that as RC got smaller, that RC, the radius of the cation, got smaller, the ability to contact the anions was impaired, so to speak. So we know that for a specific coordination number, there's sort of a, or we can establish a critical or minimum radius ratio for where you will have contact between the cations and the anions. So this figure shows sort of the general range for the cation anion radius ratio and how that range is related to the coordination number. So for a coordination number of 2, where you have the cation in contact with 2 anions, well, the cation anion ratio, radius ratio, must be less than 0.155. As we move to the next one, for a coordination number of 3, so we have a single cation being in contact with 3 anions. If the radius ratio is between 0.155 and 0.225, then that's possible. That's a possibility. Or having a coordination number of 3 will sort of occur if you have that radius ratio range, if you're within that radius ratio range, and so on. And we can go down to coordination number of 5, 6, 7, 8 as well. Alright, here you have the ionic radius of several different cations and anions, and note that the ionic radii, those radii will be different depending on sort of the charge as well. Alright, the charge as well. The charge will have an influence on the radius. Okay. So let's look at example 12.1 as quickly as we can. So the example asks us to show that the minimum cation to anion radius ratio for the coordination number of 3 is 0.155. So that's where we have 3 anions contacting 1 cation. Well, we can do this with simple geometry, because we know if we have the 3 anions contacting each other, we'll have this type of setup over here. So if I draw a line between all their centers, contacting all their centers, I'll end up with an equilateral triangle, right? ABC is an equilateral triangle, agree? So, well, what's the angle, interior angle for an equilateral triangle? Everybody should recall from math course in 10th grade, what have you, that each angle there would be 60 degrees, right? So clearly, if I split it in half, that alpha that we have here, that alpha is 30 degrees, all right? So hold that thought, and let's look at the central cation now. And I'm going to draw a line from the center of one of the anions, let's say point A, to the center of the cation. and let's call that point O. So if I draw a line from O to the line AB, then clearly, since AB is the radius, is a line from the radius going to the other radius, I'm sorry, from the center going to the other center, then OP would be tangential to either circle. And also, if it's tangential, then that angle here must be 90 degrees, right? This angle right there, the angle that the radius makes with OP, the radius from A to that point or from B to that point must make a 90-degree angle with OP. Okay, so let's look over here. I'll call the radius RA for AP for the anion, and the radius RC for the cation. So I know that AO must be RA plus RC. From A to O, clearly it's the sum of the two radii, RA and RC. And then we recall, okay, the thought that I asked you to hold was the fact that we have an equilateral triangle. So this angle here, alpha, is 30 degrees. So I know that the cosine of 30 would be the ratio of, what's cosine? Adjacent over hypotenuse, right? So it would be AP over AO will be the cosine of 30. So that's just going to be, what's AP? That's RA. And what's AO? That's RA plus RC. Okay, so I know RA over RA plus RC is the cosine of 30, or square root 3 over 2. So remember, what was I trying to find? Let's go back. We were trying to find what the cation to anion radius ratio was. So that's RC over RA. So if I look on the left here, I want to get RC over RA by itself, then it should sort of come to mind based on your experience, your algebraic expertise and experience, that hey, if I divide both sides by RA, sorry, if I divide top and bottom by RA, I'll end up with RC over RA by itself. So we see that we get 1 over 1 plus RC over RA equals 0.866, and I flip that around a little bit, play with my algebra, and I'll get RC over RA to be 0.155.